Hello everyone, my name is Fusang from Institute of Software, Chinese Academy of Sciences. I would like to share our recent work on behalf of all co-authors. The title of our paper is Your Smart Speaker Can Hear Your Heartbeat. This is the outline of this talk. It consists of 3 parts, so let's begin with background and motivation. Vital sign monitoring is a common practice amongst medical professionals and plays a critical role in assisting clinical diagnosis, assisting the overall health of a patient. Traditionally, dedicated equipment operated by professionals is used to monitor the vital sign. For example, respiration is usually monitored by EPPG and heartbeat is monitored by ECG. While the achieved accuracy is high, these devices are usually expensive and need to be operated by professionals. Smart speakers such as Amazon Echo and Google Home are becoming more and more popular in home environment. Samsung and Huawei are also following this trend to launch their smart speaker products. It was estimated that more than 200 million smart speakers have been sold until the end of 2019. And this number continues to increase every year. Wearable sensing becomes a hot research area and a lot of wearable sensing-based vital sign monitoring systems are proposed. So we have a question, can smart speaker become a platform to host home health monitoring applications? The answer is yes. So let's see how to use acoustic signal to monitor vital sign. Our system mainly consists of 2 modules, FMCW signal processing and heartbeat extraction. The smart speakers transmit FMCW chirp signals. These signals hit the target, get reflected back, and received by the microphone. The first module, FMCW signal processing, there is a runtime delay from the signal. It's triggered to be sent until the signal is actually sent out. The second module is heartbeat extraction. The heartbeat information and respiration information as well as the noise are mixed together, so we need to separate these signals. There is a system delay when transmitting an audio signal using the smart speaker. This is because the audio signal is put into a buffer first and then transmitted out by the speaker. This random delay can cause the reflection path to appear in front of the direction path after signal mixing and filtering operations. So we carefully design a virtual transmission signal and mix it with the received signal to cancel out the system delay. If the heartbeat-induced chest displacement is 0.5 mm, the phase change can be calculated as following equation. The phase change is around 16 degrees. However, one big challenge is that the phase change of the signal caused by heartbeats is submerged by respiration-induced signal change. Respiration produced 10 times larger chest displacement than that produced by the heartbeat. We observe that heartbeat, respiration, and even small body movements can induce phase variation of the signal. We categorize different displacements of body movements and their frequencies in the table. So we employ a signal time frequency analysis technique that can decompose the signal into a superposition of independent frequency components. To obtain heartbeat intervals, we then employ a dynamic heartbeat segmentation scheme by applying the EM algorithm. As shown in the figure, we plot the segmentation results obtained. It can be observed that the segmented heartbeat intervals are consistent with the ground truth ECG signals, and with only a small 0.05 second average error. So finally, we demonstrate our sensing system. To summarize our work, we enable smart speaker to monitor subtle human heartbeats in a context-free manner for the first time. We believe the context-free sensing-enabled smart speaker has a great potential to realize more useful applications in our everyday lives. So thank you for your attention.